Today we are going to look at solving second degree equations. Now, basically, we're going to take two skills that we should be fairly good at and apply them to second degree. Now, I could ask you to use your polynomial skills to do a third degree, but that's just nasty, but it is possible. So, first skill that we're going to talk about is factoring. We should have the ability to factor all of these expressions. The type of factoring is this one, x squared minus 1. Alexis? Difference of squares. Our shortcut for difference of squares is write the conjugates, take the square root of both terms, and write the conjugates of them, i.e. different signs in the middle. You can do the decomposition method of factoring, two numbers that multiply to -1 add to 0. I don't ever do that myself, but it is possible. Here, what's the first step you're actually supposed to look for before you do any factoring? Look for common factors. I have x squared that is common, leaving me with x minus 1, no more factoring available. The third one, I have no common factors. I am doing the product sum method in this case. It's a trinomial. Two numbers that multiply to 7 and add 6. So don't forget that 7 is the product of 1 times 7. Because this is a 1 in front of your x squared term, you can use a shortcut. Our numbers are 6 and 1. The shortcut is just x plus 6, x plus 1. We are able to do that. We are able to do that because this guy has a 1. If you explode this, which I'm going to do in the next one, you will get x plus 6, x plus 1. The product sum game here, we are looking for two numbers that multiply to 2 times -9 and have a sum of -3. Those two numbers are -6 and 3. I cannot write x minus 6, x plus 3. That shortcut doesn't work. There's a 2 there. I'm going to blow it up. And perform my decomposition method on it. The common factor for the first two terms is 2x. Common factor for the second is 3. Now, if you want to do a trial and error with that, it is possible to factor with trial and error. Factors of 2 are easy. Now you just got to figure out the factors of 9, how to put them into this to get your -3 in the middle. Now this one is the one that throws people the most, because we always forget the first thing that we look for is there a common factor. It's a third degree function. But I can take a common factor of 3 out, and a common factor of x out. Our product sum is 2 and 3. Those are 1 and 2. Now, I'm going to show you a possible method. If you are you're comfortable with decomposition, I'm fine. I look here, I'm going to leave that 3x out. One factor is going to start with a 2x, and another factor is going to start with an x, because that's going to give me 2x squared. I know that these guys are going to be 1 and 1, because those are the only factors of 1. Now I just got to put positives or negative signs in here, so when I multiply this out, I'm going to get a positive 3. That's what I call the trial and error method. It works really well for that one. It doesn't work so well if you've got multiple factors. Like 4x squared plus 9x plus 12, or plus 13, I'm not going to do it with that one. Too many factors. Now, this should not be news to us. We're going to apply our factoring skills to second-degree trig equations right away. Now, this is also not new to us. We have two trigonometric equations here. They are first degree because they are raised to the power of 1. We are going to perform our solving, special triangles if we can't, calculator if we can. Cos x is equal to square root 3 over 2 when we solve it for cos x. Hey, that's our special triangle, so my reference angle is pi over 6. Again, I have mine in my head. If you have to look at it, I don't really care. That is what you need to do to get through this. Cosine is positive in 1 and 4. Our solutions are pi over 6 and 11 pi over 6. Okay, so again, exactly what's on the test on Monday.
Hello.
Hello.
I just missed something today.
And I have no idea what this is for.
Yeah.
It's hiding from me too.
Oh.
Now, the only difference here, well, there's two differences. When we solve for tangent x, okay, 1/2 is on our special triangles, but it never worked. We don't have that form x. So we are going to take my reference angle is equal to the inverse tangent of positive 1/2. And now I'm asking for real numbers. Unless I ask you, and I say degrees, always talk to me in radians. Who's got a calculator handy? Inverse tangent of positive 1/2. It'd be about 0.4, 0.5, something like that. .46 radians. Tangent is positive, or tangent is negative in quadrants 2 and 4. So the answer in quadrant 2, backwards, I minus our 0.46, the answer in quadrant 4, 2 pi minus 0.46. Now, you're not quite done. You're after general solution for this, because it is all real numbers. This is the one as tangent. We know that is pi units apart. So all I'm going to do is I'm going to take my solution in quadrant 2 and add pi in. So that means all those half rotations around my circle, or that. Because that includes the 5.82 in there. Again, these are the two skills that we have from previous to apply to our second degree trig equations. So here we have 3 trig equations. Now there is one thing that we have to talk about is what the heck is this cos squared x? That is a shortcut for is a shortcut that instead of writing cos x in brackets and square it, the accepted notation for this is writing as just cos squared x. So anytime you see this, you need to interpret this. Now, I look at this and I go, okay, I'm just going to work with cosine here. But essentially what this is asking for is just the factor something like that. I can replace cos squared x or cos x with y squared. Well, that's exactly what we just did on the page before. Now we know that we can factor that one, and then I'm going to go back and I'm going to plug in my cos instead of y. I prefer, because it introduces less concerns, I prefer to factor cos squared x to go, I see it's a difference of squares. My variable is cos x. So my variable will take the square root of both sides and write my conjugates. So I'm going to go from this step without those intermediate y's. Okay? Now, if you do that, that's a perfectly valid way of solving this. Again, this one here can be thought of as y squared plus 2y minus 3. I replace my tangents with y. Two numbers that multiply to -3 and add to +2. Or those are y plus 3, y minus 1. So here I am doing it just as I said before. I'm factoring something that we had before. Since I said y was equal to tangent, we actually factor that out to tangent squared x. Nope, try that again. Tangent x plus 3. Tangent x minus 1. Again, here we have cosecant squared. I could replace cosecant or replace the cosecants with y. I'm not going to. I'm going to treat my cosecants as my variable, but I still do a product sum game. Product is 12, sum is -8, that's -2, -6. I've treated this just as I would with y. I've written cosecant in. So I think this is one we should get into the habit of, is treating the cosecant as your variable. What's common to the first two terms? A 3 cosecant leaves me with a cosecant x minus 2. Oops. What's common to the second two terms? A minus 2. Also leaving me with a cosecant x minus 2. So, our first step, like if I asked you to solve a second degree polynomial, is to factor the polynomial. Well, here we have second degree trigonometric functions. We factor those second degrees. Is there a question with my writing?
Yeah, like they're really.
Where are we? Here or here?
For x is it minus 2, both of them?
This one? Yes. Cosecant x minus 2. So factoring trig equations or second degree trig equations, we do exactly the same thing as we do with second degree polynomial. I could apply this to a third degree or a fourth degree trig equation. I would ask you to do exactly what we did for third degree and fourth degree polynomials. Now, the next step, if I was asking you to solve this second degree polynomial, we've got it factored out. Well, the only way that these two equations, these two factors are going to equal to 0, multiply to 0, is if that guy's 0 or if that guy's 0. Well, it's the same principle here. The only way this solution works is if that one is equal to 0 or that one is equal to 0. So we factored it out. Okay, so we factored it out. Well, I got it. What makes this one 0? What makes that one 0? So all we're doing is our understanding of the 0 theorem. What is that called? Doesn't matter. We're looking for where cos x is equal to 1 and where cos x is equal to negative 1. So in this case, cos x is equal to 1 at that point. Cos x is equal to negative 1 at that point. Again, that's our understanding of our unit circle. This point is 1, 0. This point is negative 1, 0. So our cosine is 1, our sine is 0, our cosine is negative 1, our sine is 0. So we have two solutions for this. X is equal to 0, x is equal to pi. And it would be 2 pi, although my domain is only asking for up to, but not including 2 pi. So we're applying, again, it's nothing difficult. Sorry, maybe it is difficult. But it is applying two concepts or two procedures that we should know from before. I can't actually remember what we factored that out to. So, first step, did your factoring. Okay, the only way that this equation, the way it's written, is going to equal to 0 is if this factor is equal to 0, and that factor is equal to 0. I'm going to do this one first because it's a special triangle. Our reference angle is pi over 2, or sorry, pi over 4 off our special triangle. Tangent is positive in 1 and 4, sorry, 1 and 3. So quadrant 1 is pi over 4. Quadrant 3 is pi pi. Our basic understanding. Again, once we're at this point, this is what we talked about the last couple of days, last week. Tangent x is equal to minus 3. Minus 3 is not one of our numbers. So the reference angle is equal to the inverse tangent of 3, just like we did before. Inverse tangent is 3, please. Probably about 1.5-ish, 1.6 maybe. I don't exactly remember. 1.25. Thank you. Again, tangent is negative here and here. So pi minus 1.25 would be 1.79. The solution in quadrant 2 is 1.79. And in quadrant 3, it is going to be 6.01. No, sorry, 6.03, sorry. Again, I don't want you to stress on this. We will be asked to solve this. Now, could you solve these graphically? Yep. But not something, the graphically part we can do fairly easy. And I'll be very honest with you, the way that the diploma is written, there is no way to solve these graphically anymore. It's very difficult to solve these graphically because the questions are asked in such a way is they force you to solve this. Okay, they might ask for what A and B are, something like that. I'm not trying to remember how they do it. Because they have had in the past is where they make mistakes. That's not something that happens anymore. But they do ask in ways that do not allow you to graphically perform an operation. Now, all right, what did we factor this out to be? That work? I think it does. Okay, now here, well, it's the same principle to start with. We set those two equal to 0. Now, we are able, that might be a little hard to see, but we are able to do this one without turning it into sine. Cosecant is hypotenuse over opposite. But we are not able to do this guy. So we have sine x equals to 1/2 here, and we have sine x is equal to 3/2 here. I'll talk about it in a second. All right, reference angle, where is sine x? Equal to 1/2 r/6. Sine is positive there and there. Solution 1 is pi/6. Solution in quadrant 2, 5 pi/6. Yeah, I'm hoping that everybody's comfortable with that. Now, why does this one not have a solution? What's that? It's bigger than 1. It's outside the range for sine x. So, since this is larger 1, all we do, okay, I don't have a solution. If I tried to punch inverse sine of 3/2 into my calculator, unless you're Rory's calculator, it's going to say error. Rory starts to speak imaginary numbers. Don't do that. Okay, as soon as you see that I, stop. We are never going to have an imaginary number in 30-1 or 2. So the solution is here. Now the general solutions are easy, since we've already got everything else. These were our solutions. The general solution for this guy could be written as 0 plus 2 pi and pi plus 2 pi, but again, they're only pi units apart. So my solution for this kind of looks silly, doesn't it? We don't write zeros very often when we're adding, so the solution for this one is just pi. I like these diagrams to remind me, okay, that's only pi units. For this one, I forget what it was. Again, looking at our tangent here, again, pi units apart, pi units apart. So we have two equations that we have to draw. We have to do it for this guy, and we have to do it for that one. So we had pi/4 plus pi n, and 1 point, oh, for Pete's sake, I forget what it was already. 1.25 plus pi n. And since I don't really want to write and all the numbers twice, I do that with brackets. This one here, we need to. We have two different quadrants. They're not opposite from each other. So I have to do pi/6 plus 2 pi n and 5 pi/6 plus 2 pi n. So combining two skills that we already know, factoring and solving first-degree trig equations. Now, is it possible to solve this one a little bit differently? Yes, because it is a difference of squares, I could just go cos squared x is equal to 1, take the square root of both sides, and then I'm there. Okay? But we often forget to put a positive or negative sign, negative sign in front. This is no different, except the main is all real values. So I'm asking for the general solution of this one. Sean, two numbers that multiply to -6 and sum to 5. Okay, so again, I'm just going to do a shortcut. I'm going to do my shortcut. Please feel free to explode this one. I know I'm going to have a factor that starts with cosec, or two cosecs, and a factor that starts with cosec. My factors of 3 are 1 and 3. I just have to figure out how to get 5 out of them. Okay. So all I'm doing when I'm doing my shortcut is I know my factors of 2 are 2 and 1, and my factors of 3 are 3 and 1. And I did it in right away. I could have put my 3 here, and I would have done my multiplication and found, no, that doesn't get me to -5, or +5, I should say. Okay. Our solutions, 2 cosecs minus 1 is equal to 0, cosecs plus 3 is equal to 0. I can do this one easy. Cosecs is equal to -3. Oh, again, cosine has a range from -1 to 1. No solution. Does tangent have that problem, or cotangent? Is there a solution for tangent x is equal to -3? Yes, because tangent has a range of all real values. Now, we really haven't talked about cosecant and secant. Secant and cosecant have a range from infinity to -1 or 1 to infinity. So I actually can't have, if I had cosecant x is equal to 1/2, there's no solution to that. But we see that when we flip it over and go, oh, that's sine x is equal to 2. Doesn't work. So we like using our angles that give me, they give me special triangles. Reference angle for cosec is equal to 1/2 is pi over 3. Cosine positive in 2 quadrants, 1 and 4. And we're not quite done. We just did our solving between 0 and 2 pi. We went from -infinity to infinity, so x over pi over 3 plus 2 pi m, and 5 pi over 3 plus 2 pi m. Now, if we think about this, okay, and if we were to think about this graphically, we have the ability to graph each of those functions. Okay? 2 at cosec minus 1 has a midline at, oops, I put that midline in the wrong spot. Got the midline at -1 and has an amplitude of 2. So it's going to cross the x-axis. So you're going to have solutions. Cosec plus 3 has a midline at 3. It only has an amplitude of 1. So it's never going to intersect with the x-intercept. Therefore, there are no zeros or no solutions to that equation. That's a graphical explanation why I toss out this guy. So if you think about it graphically, you can give me a quick sketch. You see that guy has a solution because it does cross, this guy doesn't because it doesn't cross. Well, I see Sean's already started on his homework. Page 596 in your textbook. What you can do, because we have